I found this video called High Schooler Explains the Fourth Dimension. It got like 1 million views. So I'm making this video. If I don't get 1 million views, I will become preposterously angry. Anyways, today is November 23rd, 2024. So as of right now, I'm an 8th grader. And to be clear, I am not an expert on this stuff. I barely know the surface of these topics, so if you're researching this, please do your own research. I am not.
My God, it's Albert Einstein!
Anyways, let's first define the fourth dimension. What exactly is it? Is it time? Is it space? Is it a four-value vector quaternion? Well, in 1908, a mathematician, not a theoretical physicist, named Hermann Minkowski theorized that the world is actually an enormous 4D fabric that is known as the Minkowski space, or that's what its name. It travels along the fourth dimension as time progresses. So basically, everything changing is just a three-dimensional slice of this gigantic 4D fabric. And yes, that means us, our thoughts, are all part of this Minkowski space. Quite a grim concept, if you ask me. This theory is known as space-time theory. It was continued by Albert Einstein in his theory of general relativity, how gravity and velocity bends time in space, all those weird sciencey stuff. Also, in 1827, a Swiss mathematician named Ludwig Schoffe theorized that Euclidean geometry could be applied in higher dimensions than just Euclid's intended 3 dimensions in his original Euclid's Elements. Continuing his work, Charles Howard Hinton theorized the tesseract, basically a 4D cube. You could also call it an 8-cell or a hypercube if you like. Anyways, now let's move on to what exactly this tesseract is. Similar to how circles are to spheres and how squares are to cubes, the shape is simply just 2 connected cubes with a length along the fourth dimension, or the W-axis as it's called. Similar to how cubes have 6 sides of squares, the tesseract has 8 sides of cubes. This has an interesting effect on what it looks like when unfolded, which we'll talk about later. Now, what does this shape even look like? This. Now, you might wonder, why are there so many pictures of tesseracts? Why are they all different? Well, let me explain. This is a picture of an orthographic tesseract. Some might say, hey, this isn't a tesseract, this is just a octagon with a weirdly shaped star in it. Well, this is not a tesseract, it's a projection of it, an orthographic projection, an isometric orthographic projection of a 4D object onto a 3D display, which is then projected orthographically onto a 2D display from an isometric angle. That was a mouthful. Anyways, to give you an example of what isometry is, this is the cube. It just looks like a hexagon with a dot in the middle. I also have this GeoGebra calculator, which shows a perspective projection of an orthographically projected tesseract. And as you can see, these are the 2 cubes and they're connected with these lines. You might be wondering, where are the 8 cubes part of it? Well, check these boxes. You can see it selects the different cubes that are part of it. There's these 2, these two, yeah. You can build up from this dot as I move the slider to this line, and then if you drag it more, you get a plane, and then you drag it more, you get a cube, and if you move along, you have the tesseract. Some of you might be wondering, what exactly is orthographic projection? You know how in perspective, when things are farther away from you, they get smaller? In orthographic projection, everything just stays the same no matter how far away it is from you. Isometric projection, on the other hand, is just a type of orthographic projection that basically aligns the axes as a type of 3-point star and having objects drawn according to that. And also, you can't actually achieve orthographic projection in real life with something known as a Fresnel lens. Basically how it works is that it only projects what's in front of it to the focal point using prisms on the lens, creating orthographic projection. But since there's an orthographic projection of a tesseract, can't we have perspective? The perspective projected hypercube. You've probably seen this representation a lot when you search up 4D object. You'll see all these cool arts of this cube inside of another cube connected. The reason it's like this is that it's getting smaller as it goes along the 4th dimension, similar to how things get smaller in our 3 dimensions as it goes along the z-axis. This is in contrast to the 2 same size cubes in the orthographic projection. This is what 4D objects looks like to 4D beings. Since 4D beings have 3D vision, this is how theoretically 4D beings see due to their 3D vision if you had 4-dimensional light particles. Similar to how our eyes see in 2 dimensions, 3-dimensional light particles coming to our eyes. Anyways, a lot of you have probably seen this video of a rotating tesseract with all the weird warping cubes going in and out. A lot of you are probably confused by this and how it's a rotation. I'll get to this later. And you might be wondering, where are the 8 cubes that are part of this tesseract? Well, I have another GeoGebra calculator which basically allows you to check and uncheck different cubes part of it. Anyways, you have cube 1 and 2, which are the large one and the small one. And then you have these ones which are at the top and bottom sides, these ones front and back, and these ones left and right. So those are the 8 different cubes that make up a tesseract. Well, this here is actually a 3D orthographically projected 4-dimensional perspective projected tesseract. Wow, that was a mouthful. There's also these sliders here, but I'm not gonna touch those for now as they are rotation, and we'll get to that in the next part. So I found this video of a rotating hypersphere, which is basically just a 4D sphere, as a circle is to a sphere is to a hypersphere. Anyways, this isn't really a true hypersphere, just because a true hypersphere would have infinite amounts of spheres inside it. This one has a finite amount, so it's not real, but it does give you a pretty good outline of what it would look like. And by the way, this is still just a perspective projection of it. Anyways, similar to how you get a T-shape when unwrapping a cube, you also get a similar T-shape when unwrapping a hypercube. This is what an unwrapped hypercube looks like. This would actually be hollow, since having just 8 cubes wouldn't have it filled in, it would be hollow. But what would a 4D tesseract look like in real life? Well, here's an example. Yeah. It's just a cube. Well, let me explain. Say you have a 2D plane and a 3D object aligned to that plane. If you drag the cube through that 2D plane, a creature on that plane would just observe a square that at one time exists and at another it doesn't. So this is what it would look like in 3 dimensions. If you had the tesseract travel along the 4th dimension, this cube would at one time exist. At another time, it wouldn't. It would just be gone. This is similar to what happens when you have a sphere move through a plane. But when you have a hypersphere moving through the 3D plane we live in, it would just start as a single point, move into a large sphere, then go back to that single point as it travels along the 4th dimension. This is similar to how in 2D, when you move a sphere through it, it would start as a single point, expand to a circle, gone. That's what happens. Anyways, let's start what these rotations would look like in projected form. Of course, when you rotate a 3D cube and then get the 2D cross section of it, it would become weird. Like you'd see hexagons, all those weird stuff, and the 2D creature would be really confused when they see that. Like, what? Why is it warping all around? For 4D, it also looks pretty strange. Here I have this GeoGebra calculator, another one, which has these rotations XY, YZ, XZ, XW, YW, and ZW. Those 6 knobs just control the rotation of it. And you might be wondering, why are there 6 different ways you could rotate it in 4D? Can you only have 4, like how you could rotate things on the X and Y and Z, and then if you're in a 4th dimension, you rotate it on X, Y, Z, and W? Not exactly. This property is actually only exclusive to the 3rd Euclidean dimension, which we live in right now. So how does rotation even work here then? In fact, rotations are based on planes. For example, if you had a square on a 2D plane, you can't really rotate it on the x-axis or the y-axis. That would bring it into the 3rd dimension. But how does this work? When you're rotating the square, you're actually quote-unquote rotating it relative to the xy plane. In 3D, rotations are said to be along x or along y or along z. That's not exactly correct. Correct and not correct at the same time. In reality, rotating along the x-axis is actually rotating relative to YZ plane. So because of this, we have 6 ways you could rotate it. Fun fact, the 3rd dimension is the only dimension where you have the same amount of rotation planes as the amount of axes you have. This is because the normal vectors of each plane in the 3rd dimension is directly aligned to another axis in that dimension. Like if you had the xy plane, the normal vector of that xy plane is directly aligned to the z axis. So yeah, that's why it's called rotating along the z axis. Anyways, let's look at some of these rotations. As you can see, as you rotate along the xy plane, it just looks like a normal rotation. The yz, it just looks like a rotation, like an actual rotation. But if you start to rotate on the xw, yw, and zw, you start to see the weird things that you saw in the rotating tesseract video. It's moving all sorts of weird ways, with the cube warping like this and doing all this weird stuff. I'd like to show you an interesting thing that happens if you look at it from the front side. Since this isn't prospectively projected onto the 2D screen, you can get it perfectly like this. I want you guys to see what happens when you rotate it. It just looks like a 3D cube rotating. It just looks like a regular 3D projection of a cube onto a 2D screen. But if you rotate it on these other axes, it starts to do these weird scaling things with wonky stuff happening, all that weird stuff. Now, this is actually what 4D rotations would look like to us 3D creatures. If a 4D object was rotated into a 3D world, that's what it would look like. You could see it skewing all over the place. Now, this is kind of a bad visualization since it's there's no surfaces you can really go off of. So let's go back to the previous hypercube that we had right here. Now, since this thing has surfaces, it's much easier to visualize. This is just like a regular cube, and then if you rotate a little bit, it starts to look like a skewed cube. Rotate it even more, it does all sorts of weird stuff. It just looks like a weird warping around 16 vertices shape. Now, I have a better visualization for this, which is a video. You can see the cube tesseract just expanding 3D rotations, and as it rotates in the 4th dimension, it does all sorts of weird stuff, weird warping. This is just a better visualization of what would happen.
Of course, with the hypersphere, it's similar to a sphere rotate. There would be, of course, matter that just comes out of nowhere, but you wouldn't really see that. Also, this is what rotations of a tesseract would look like orthographically. This is a video I found of a rotating tesseract. For some reason, it's washed. I don't know why. Let's see what it looks like in orthographically. On the side, you can see that it just looks like a regular cube rotating. These are 4D rotations, and it is wonky. It is pretty weird. Similar to the projected tesseract on a 3D orthographically projected, and you can see all types of wonky stuff that happens as it rotates. Now let's move to the Klein bottle. Maybe thinking, hey, isn't this Klein bottle a 3D object? Not exactly. The 3D version of it is actually just an orthographic projection of it. It's an actual mathematical representation of it. It doesn't have this intersecting side of the tube intersecting the bottom part. In order to have it not intersect, you have to bring it into the 4th dimension. This is often said to have no volume, and that it's like a Mobius strip. If you had a 2D creature to go around it, it would never find an end. And yeah, that's not all to it. This is a visualization of what a Klein bottle looks like as you advance it to the 4th dimension. You just see the parts just going around, and they're not intersecting at all. And you can see that the tube doesn't actually intersect the bottom at all. It's at a different part in the 4th dimension. Let's see what a Klein bottle would look like rotating rotating in our 3D world. So here I have this video I found on YouTube. This is even weirder than the Tesseract rotation. I can see some resemblance to the 3D mind bubble that we have. There are a lot of channels spreading misinformation about the dimensions, like Brightside or Riddle in channels like those. For example, I found this video. It states that, oh, you can see emotions with the glowy line, you can project your mind, and no, that's not how it works. Teleportation in the fourth dimension are not the same thing. You cannot teleport in the fourth dimension, and it's not related to neuroscience. You won't see emotions. Just so you will be aware of this misinformation. But there's also been many interesting interactive games that's being created of this 4D concept. There's even this paper made by Mark 10 Bosch on higher dimensional rigid body physics. And as you can see in the visualization, there is 4D physics. Some of the games that use 4D are 4D miners. Basically, this is a 4D version of Minecraft. This guy has a YouTube series on it. If you haven't checked it out already, you should go check it out. It's also free to demos. And how it works is that it rotates your 3D plane along the 4th dimension. If you rotate it, you could technically travel along it because you rotated it. If you look at it, it does some pretty weird stuff. But this is really representative as it had its 2D features on a 2D plane, and you rotated that along a 3D object. It would look weird just like this. There's also another one made by Mark 10 Bosch, the same guy who made that physics paper called 4D Toys. It's a really cool, well, game. It's not really a game, but you could sort of VR thing where you could move around these 4D objects in 4D rigid body physics, and you could also use a slider to move around the 4D space so you could see the different parts of it. One time you'd see a small floating sphere, but in reality, if you move along the fourth dimension, it's actually just a hypersphere that is sitting on the ground. And also 4D golf. Now, this is a true crazier game based on the fourth dimension. Basically, how it works is that you play golf, and then you have to move along the fourth dimension in order to get to the different places. It's really weird. One time you would have no path to the end. The other time if you move on to the fourth dimension, you will get it. There's even a level creator. I just find that mind-boggling. It looks awesome, and I don't have any money to buy it. That's all I know on the fourth dimension. I hope you guys enjoyed a middle schooler yap about the fourth dimension for a few minutes, and see you guys next time. Bye.